Welcome to the Explainer. Today, we're going to crack the code on a problem that, let's be honest, trips up pretty much everyone who works with data tables. You know the one. What do you do when the exact number you need is just missing? We're going to break down the solution. It's called linear interpolation into some really simple, clear steps.
All right, let's make this real with a classic example. Imagine you're an engineer and you're staring at some steam tables, which is basically just a big chart full of data. You've got all these established data points, right? But the specific pressure you're trying to analyze, it falls smack dab in between two of them. So, what do? How do you find the answer you actually need?
So here's our exact situation. We know the specific enthalpy, which, by the way, is just a measure of energy, for steam at 100 bar, and we know it for 105 bar. But the one we actually need for our calculation is for 103 bar, and wouldn't you know it, it's not in the table. So what are our options? We definitely can't just guess.
Yeah, we need a reliable, logical way to kind of read between the lines and estimate that missing value. And this is exactly where a really powerful but surprisingly straightforward mathematical tool comes into play.
Okay, so the big idea here, it's called linear interpolation. And what we do is we make a really simple but incredibly useful assumption. We just assume that the relationship between our two known data points is a straight line. And once you assume that, you can accurately estimate pretty much any value that falls along that line.
So how do we actually translate that whole straight line idea into something we can calculate? Well, it all comes down to setting up a simple proportion, or a ratio.
The process is super logical when you break it down. First, you just find your boundaries, the data points you have that are above and below your target. Then you build a ratio that compares the distances between these points.
And this right here, this visual pretty much sums up the entire method in one elegant picture. Think of it like a balance scale. On one side, we have our known variable, which is pressure, and on the other side, our unknown, which is enthalpy. The whole idea, the core of it, is that the ratio we find on the pressure side has to be exactly the same as the ratio on the enthalpy side.
Let's break that down a bit. The pressure side of the equation is just figuring out how far our target of 103 bar is along the total pressure range from 100 to 105. And what we're saying is that this exact same proportion has to hold true for our unknown enthalpy value, which we're calling Hg, along its own range from 2725 down to 2715.
So we've got our proportion all set up. Now it's really just a matter of solving for that one little piece of missing information.
The left side of this equation is super easy, right? Because we have all the numbers. The difference between our target and the start is 3, and the total range is 5. So you just do 3 divided by 5, and that gives you 0.6. Now this is our key number. What it's telling us is that our target pressure, 103 bar, is exactly 60% of the way between 100 and 105 bar.
And now, we just apply that same 60% proportion to the other side. It means our missing enthalpy value also has to be 60% of the way along its range, from our starting point of 2725 to our ending point of 2715. From here, it's just a little bit of algebra to isolate our unknown value.
And there it is. After you rearrange the equation, you find that the specific enthalpy at 1003 bar is 2719 kilojoules per kilogram. We did it. We found our missing data point. But are we done? Not quite.
Okay, before we ever accept a calculated answer, there is one final, absolutely crucial step we always have to perform. It's a simple little mental check, but trust me, it can save you from making some huge mistakes down the line.
You just have to stop and ask yourself, does this answer actually make sense? Given the numbers we started with, is this result even plausible? This is maybe the most important question you can ask in any calculation.
So just look at the table now. Our number, 2719, well, it sits perfectly between our starting points of 2725 and 2715. See, in this case, the enthalpy is going down as the pressure goes up, and our answer follows that trend perfectly. It just makes logical sense.
And really, that's the golden rule here. Your final answer has to fall somewhere between your two known data points. If it's higher than the max or lower than the min, you've goofed up the math somewhere. This simple check gives us the confidence that our calculation is solid. All right, so we've walked through a single interpolation. But why does mastering this simple little procedure matter so much? Well, because it turns out it's a fundamental building block.
Seriously, once you are really confident with this single variable interpolation, you unlock the ability to solve much more complex problems. We're talking problems where two different variables are changing at the same time.
Okay, just take a look at this. On the left, that's the exact problem we just solved.
Pretty simple. Now look at the one on the right. That's a double interpolation problem. Looks way more complex, right? Kind of intimidating. But here's the secret. To solve that big, scary-looking problem on the right, you just do this simple thing from the left 3 times. That's literally it.
And that really is the key takeaway here. It's not about just memorizing a formula. It's about understanding the step-by-step logic. When you have a structured approach like this, you can tackle any problem, whether it's simple or complex, and feel really confident in your final answer.
And that wraps up our look at linear interpolation. You know, it's a beautifully simple idea, but it's such an essential tool for anyone who has to work with data. So, the next time you're staring at a table and you see a gap, you'll know exactly how to fill it in. Thanks so much for joining us on The Explainer.